Welcome to this Neo4j webinar. We are excited to have our longtime partner GraphAware with us today to talk about how knowledge graphs can be applied for regulatory compliance by combining Neo4j and Hume. Hume is a GraphAware product. Now, as I was just saying, the session will be recorded and we will share the slides afterward. Please make sure you can put your questions in the Q&A section of the panel. We will answer them in the panel and at the end of the session. Now with that, I guess I'll hand it over to you, Michael.
Thank you, Eva, for the introduction, and hello, everyone. Let's jump right in. What we're going to do today is I'm going to quickly introduce GraphAware and the speakers. I will then frame the talk and explain why we are talking about this topic in the first place, before handing over to Alessandro to introduce us to his point of view on knowledge graphs. Vlasta will then walk us through a sample knowledge graph based on a real project that we have done and show a few simple examples of how these knowledge graphs can be leveraged to save time, costs, and reduce compliance risk. We will then conclude and open up for Q&A. So just a brief introduction. We believe at GraphAware that in maximum 10 years time, let's say, graphs will be used in every single organization in the world, and we want to be the most trusted partner on everyone's graph journey. So our mission is to enable organizations to gain competitive edge through the application of graph technologies. My name is Michael. I'm the founder and CEO of GraphAware, and today I'm joined by Vlasta, our lead data scientist, who's done bulk of the work on the real-life project that this talk is based on. He will present towards the end of the webinar. And finally, the kind of core of the talk, our chief scientist, Alessandro Negro, will share some of his experience on knowledge graphs and some of his expertise. He's just celebrated 6 years at GraphAware, gaining hands-on experience with graph-powered machine learning applications. And so I want to talk about 30 seconds this book where this experience is distilled. It is real. It's finally printed. I'm holding it in my hand. We're very excited about it. So if you're a practitioner or data scientist, machine learning engineer, graphista, whether aspiring or seasoned, I highly recommend picking up a copy of this book. So let's talk about regulatory compliance. It is the goal that organizations are trying to achieve in their efforts to ensure that they are aware of relevant laws and policies and regulations and take steps to comply with them. It is the most common industry that's talked about in the context of regulatory compliance is banking and financial services. And indeed, there are countless regulations that banks and financial services companies have to comply with. Some of you will be well aware of the PCI DSS, which is the Payment Card Industry Data Security Standard, many, many other regulations in the US, the Patriot Act, Consumer Protection Act, and so on. In Europe, of course, the GDPR that everybody knows about, that has consequences also for institutions outside of the EU. There are many other industries, though, and other kinds of organizations that are heavily regulated, from oil and gas, car manufacturing, to insurance, air transportation, and pharmaceuticals manufacturing, and the list goes on and on and on. And of course, we should not forget all kinds of government institutions, including law enforcement and other kinds of security agencies who protect the public from all kinds of threats, but have to comply with the law and other regulations while doing so. In fact, the idea for this webinar was born after we completed a real-life project implementing a knowledge graph for regulatory compliance for a major law enforcement agency. And of course, we should not forget to mention that every jurisdiction has different compliance requirements and reporting standards, which adds to the whole complexity of the compliance challenge. But compliance is not only widespread, it is also a growing challenge. An article from The Economist, which is now 2 years old, titled "The Past Decade Has Brought a Compliance Boom in Banking," says that compliance staff makes up 10% or more of the workforce in large banks. In the same article, we learned that at a major US multinational bank, the compliance staff made almost 15% of the total workforce in 2018, up from 4% in 2008. So that's 4x increase in 10 years. Only for the financial services sector, thousands of new regulations have been introduced in the last 20 years. And one of the reasons, by the way, is rapid digitalization and increasing dependency on partners for providing business services. In other words, everything in the world is becoming more and more connected. So I'm glad that you're listening to a Graph webinar here. And of course, it wouldn't be a 2021 webinar without mentioning COVID-19, of course. The pandemic introduced even more compliance challenges as businesses had to rapidly adapt to the changing situation. So remote working, perhaps from a different country, is one of the challenges that has been discussed, one of many challenges that have been recently discussed. So regulatory compliance is widespread and growing challenge. So, it's not hard to imagine. It's also a very expensive challenge. There's an estimate I found from Deloitte that banks are spending $270 billion per year on compliance globally. And that was in 2017. The costs make roughly 10% of the total operating costs of the banks. And in the same Deloitte report, they estimate these numbers will have doubled by end of next year, basically. That doesn't include, of course, the cost of non-compliance, which could be much bigger. In an extreme case, it could destroy the organization altogether. Just to mention a few examples, in 2018, there was a GDPR incident at a major British airline for which the ICO proposed a £180 million fine. There's another incident, a US-based credit reporting agency. There was some data stolen, about 150 million customers' data records. In 2017, the FTC fined them $700 million, and the list goes on and on and on. There's an excellent 2017 report from Capgemini titled "Regulatory Compliance is a Data Management Game." The top challenges cited there are that are data overload, high costs of maintaining large amounts of data, and for us, most importantly, the difficulty in extracting information from the data. So is regulatory compliance an information challenge then? Well, before we answer that question, we'll have to have a look at one undisputable phenomenon, a fact of life issue, if you wish, and that's the presence of continuous change. This is the real challenge, as legislation and regulation changes constantly, which of course has an impact on organizations. And organizations themselves change, right? There are structural changes which impact accountability and responsibility. And there's also an element of change that comes from within the organizations as they strive for continuous improvement of their compliance, governance, and accountability mechanisms. So with every change that occurs, questions pop up. For this particular change, what instruments, controls, and processes are impacted? How are they impacted? What's the impact? And most importantly, what should we do about that impact? But not only those, there are many more questions that stem from the fact that there's ever-present challenge. And so to find the answer to all those questions, we believe that information isn't enough, because information is just data which is well organized in a data warehouse, for example. Well, we have seen a lot of data warehousing projects with lots of information in those warehouses, but very few answers to real business questions. And I'll hand over to Alessandro.
Yep. So in order to answer to these questions and tackle all these challenges, we need to do a step more and speak instead about knowledge challenge. That actually translates in how to gather, explore, and analyze the data and information available to create a proper knowledge framework that is that in the right hands can solve all the issues just mentioned. And this is true not only for regulatory compliance, but for many different tasks in various domains. Think about biomedicine, law enforcement, fraud detection, recommendations, and so on and so forth. They all require you to properly deal with all the knowledge available. Luckily for us, this is quite a common problem for which many solutions have been proposed. And one of them is becoming predominant, and it is based on graphs. And that, for obvious reason, is referred as knowledge graph. I would like to introduce then a few concepts related to knowledge graphs before getting more practical with our demo. As a disclaimer, I have to say that what I'm going to present in this part here is the GraphAware's point of view around the knowledge graphs, not a generic truth. Because even though everybody agrees on the relevance of such type of graph for solving complex problems in machine learning and not only, there are no standards or very few around that. So many different ideas are coming from different sources, and as a consequence, there is still a lot of space for discussion. So I'm going to be talking about the reasons why knowledge graphs erupted in the machine learning space. Then we will try to formalize a definition of knowledge graphs. So we will describe what they are and how they can be implemented and used in a generic way. I'll also briefly introduce Hume, that is, as Eva mentioned, the GraphAware knowledge graph platform solution built on top of Neo4j. And then we'll present a concrete application of Hume and in general knowledge graphs applied to the real and tedious problem of regulatory compliance. That is our main topic today. So let's start from the goal of the knowledge graphs with their why before describing what it is. This will make the definition and what will come next much easier to understand. So, supposing that our broader goal for machine learning practitioners like us, or for companies like us, and I think for many of you and your companies, is to build intelligent systems. But let's step back for a second and think about what is intelligence. Well, without searching for complex answers in psychological or philosophical books, the dictionary defines it as the ability to acquire and apply knowledge. Think about us as humans. For a very wide range of activities, we make decisions based on what we effortlessly and unconsciously know or believe to know about the world. So our intelligent behavior is clearly conditioned, if not dominated, by knowledge. The main question we are trying to answer here, the main why, is then how can I represent the knowledge so that an autonomous agent, humans as well as a mechanical or electronic agent, can behave intelligently? Knowledge representation is clearly then a key topic in the area of artificial intelligence. And it is concerned with how knowledge can be represented symbolically and manipulated in an automated way by reasoning programs. Mikkel before introduced let's say other goals and challenges more specific with the regulatory compliance topic, and that can be reconducted to the broader questions. They were, how does this change in regulation can impact my processes? Which guideline is most likely out of date and need a review? So these considerations, these questions can drive us to further constraints in the definition of the requirements for our knowledge framework. We can also require, for example, that the same representation should be suitable for humans and for machines, so that we don't have to store and keep them in sync, the same information actually twice in two different ways. This representation should be holistic, in the sense that should allow me to store the entire knowledge I have coming from different data sources, from different data formats. And this is the only way in which I can condense in the knowledge framework all I know. And last but not least, it should be efficient, which means that it should be fast to be accessed and shouldn't require a lot of space. Of course, this is definitely an ambitious goal, or actually a set of goals, with a lot of questions and constraints, all related to the importance of the creation of a proper knowledge base, easy to manage and access. So trying to answer to similar questions, two guys formulated an hypothesis. So the structuring of knowledge in a graph can be seen as the construction of a knowledge-based system integrating knowledge from different sources. So despite of the complexity of the problem, someone found a simple answer, a knowledge graph, actually without mentioning it. Of course, I agree with this sentence, but do you know what shocked me? Well, the fact that this was formulated in the 1988, so more than 30 years ago. Of course, we were not ready for the time, to put this simple concept into practice. The technology was not there, and we didn't have Neo4j, of course. But from now that the problem is clear and the constraints and the broad definition of the solutions are in your head, we have to deep dive in the description of what a knowledge graph is. And here is where things get a bit more complicated, because the topic is so fresh that a broadly accepted definition is still missing. But wait for a minute, because I said fresh to something that actually was mentioned in 1988. But of course, here I'm referring to the new trend that started a few years ago, in which we consider the knowledge graph as a real enabler of the artificial intelligence. So starting from the previous sentence from these two guys in 1988, actually we could say in the simplest way possible that a knowledge graph is knowledge in a graph. That we can say will be a very accurate definition to explain to my parents what I do for a living. I put knowledge in a graph, but not enough if we would like to productize it, if we have to create an entire system using it to deliver value to companies, to deliver value to end users. So among the many possible definitions, there is one that I really prefer, since it provides answers to the previous questions and give a clear guidance even to the implementation. So assuming that, as we said before, the knowledge graph is a representational framework. It consists of a set of interconnected type entities and their attributes representing a real world entities such as people, role, documents, obligations, risks, as we will say later, and any relationships among them. According to this definition, it can collect and organize the data from multiple data sources, providing the flexible and extensible access patterns that we need. So it can represent the only way to manage the world of enterprise data in full generality. And more interestingly, it is domain agnostic. So it works for any organization, for any scope. So let me add also that major companies such as Google, Yahoo, Microsoft, and Facebook have created their own knowledge graphs that empower multiple advanced services. So we can definitely say that, that the use of these knowledge graphs is becoming the norm rather than the exception. And there is a clear reason because this is happening. Well, a set of reasons. The knowledge graph approach allows not only to store relationships among entities, but sometimes these relationships are created automatically while we are storing this data in a very simple way, in a straightforward way. And in the demo, we will see how this is possible. Moreover, it provides multiple access patterns, because in a graph, every single node and every single relationship could be considered as an access point for your analysis. And this is definitely means that the knowledge graphs can provide you an efficient access to it. And well, knowledge graph can also easily store contextual information, apart from all the above, naturally. So it represents a concrete enabler for complex machine learning processes, and in general for artificial intelligence. Let me add also that as it will be clear in the demo, it is suitable for humans and for machines. That, of course, it was one of the key requirements that we had before, because we wanted humans and machines to share the same knowledge representation so that we can avoid to store it twice. So from this, it's clear that actually a knowledge graph could be the right framework to address our key questions, to help us in our challenges. So now that the definition and the description of the knowledge graph approach, and and now we define also some of the constraints very clearly. We need to discuss how to operationalize it, which translates in how to work day by day with it and use the knowledge graph to get a real value out of your knowledge and deliver it to the end users or your end customers. So in this path, the next logical step, one of the most critical steps, is to decide how to physically store it. And this is, as I said, a critical aspect, since in one of our requirements, we mentioned how important it is to efficiently access to the knowledge in order to provide an adequate level of services. Imagine, for example, a real-time recommendation engine that delivers suggestions after 3 minutes. Well, it is completely useless. This is just one of the possible examples. So regarding storage, again, things are getting interesting, since as for the definition, there is no standard way for storing it properly. And the nice, well, regarding, and the simplest answer that I can give you is that you can do it in the way in which you prefer. But actually, we are here to give you some guidance. And so let's see what are the most common approaches and how to decide among them. So, well, let me say that this is one of the most controversial points, because if you ask to many people about how they are storing it, well, I'm guessing that 80% of them will answer with rich data format, or RDF as acronym. That and here you have an example on the right. The reason should be clear if you start also investigating what they were doing before embracing this knowledge graph trend. They were ontologists, they were working in university, most probably they were a semantic web expert, because in some way knowledge graph is capturing the attention of all these people that had a lot of expectations from semantic web a time ago, and now it seems that knowledge graph is fulfilling all these let's say expectations. For us, it's different on the other side, because for people like us that worked with graphs since a while, there is this new trend that is becoming more and more clear. And for us, and according to this trend, the most common way for representing a graph is as a label property graph, or LPG, for which we have an example here on the left. Well, in an LPG, we have labels identifying a different type of entities, like people, organization, as we were mentioning before, and so on. Typed relationships connecting those entities, and attributes that contain in the form of key value information about both. And as I said, you can immediately see what's the difference between them in terms of verbosity, in terms of the amount of relationships that you have to create in order to let's say to store the same set of information. That's why we prefer definitely LPG. And also there are languages like Cypher that will let you don't miss anything about SparkQL, that is the query language used in the case of RDF. So just to continue on this line, let me show you an example of a possible knowledge graph for regulatory compliance. Of course, you will see just a portion of it during the demo. Here we see the key elements that could be the main entities stored in the knowledge graph related to the regulatory compliance. And you can see obligations. You can see how these obligations are extracted from different sources like law, regulation, guideline, and so on. How these obligations introduce some risks for the company, and so on and so forth. So for a moment, imagine if you have to represent these plus all the attributes of these data, these entities in the form of a RDF. It would be definitely much bigger, if not a real nightmare. So since we are getting to an end of this overview of what a knowledge graph is, before moving to the demo, let me spend really 2 more words about what we are going to see there. Because all these generic concepts have to be translated in a platform, in a concrete system that people can use to do their job, to navigate their knowledge. And this is where our GraphAware Hume comes into play. Well, GraphAware Hume is our knowledge graph platform, and it is an ecosystem which converts structured and unstructured data from several and distributed data silos or multiple data sources and organize them in a single connected source of truth. That is the knowledge graph, actually, that will represent a new asset for the company. It provides all the functionalities that we need actually to organize, to analyze, enrich, and also visualize a knowledge graph. For example, extracting the hidden structure from the text and store it properly in the form of a graph. For example, extracting the key concept from a regulatory guideline. Merging, it can merge various data with different schema in a single data model, that is our graph model, or it can help you to properly analyzing and enriching this data that you imported actually in the regulatory compliance. This could mean, for example, aggregating similar documents, extracting automatically topics, identifying risks, and so on and so forth, or similarities among the guidelines. And finally, once you have it, you can deliver easily these insights, these wisdom extracted from them, and visualize them properly. So if since the overall process or all these processes are quite complex, what we tried to do was to decompose them in more simpler steps, I would say, that are reported here in this image. Some of them act in circle. That means that they are executed more and more until we have more knowledge to extract from the existing data that we have. So the ingestion, in this sense, that will not be presented in the demo or not extensively because it is requiring a lot of time. Well, it brings data in a first form in this knowledge graph, and then these natural language processing, enrichment, and machine learning tasks will extend the knowledge that we have, analyzing it and getting the insights and wisdom ready to be delivered by the interface that will allow you to, let's say, explore this knowledge that you have. So now it's time for our demo and see how all these words are translated in practice. If you have any questions, either wait until the end or just write it in the chat, in the question and answer chat, and we will be able to answer there before the end. So, Vlasta, hand it over to you.
Thank you, Alessandro. Let me share the screen. In this demo, is based on a real-world example or real-world knowledge graph that we built for a highly regulated government organization in the law enforcement domain. For the purposes of this demo, the data we ingested and processed is only publicly available, and we renamed or named the organization name as ISSQX. What you can see here on this canvas is the knowledge graph schema. As you might know, Neo4j and graph databases in general have a big advantage because they are schemaless, which gives them lots of flexibility. However, in case of knowledge graphs, it is very advantageous and even very important to have a schema. For example, because it allows us to build various different use cases on top of the same underlying graph database. What we can see here is the whole structure. This schema includes both structured and unstructured data. The document nodes here in the center represent the unstructured data. There are various internal guidelines, operations procedures, documentations, and so on. These were ingested, processed by the NLP pipeline, and stored in the graph. Connected to these nodes, you can see various entities such as person, location, criminal charge. These come from the NLP pipeline and specifically from the named entity recognition, which are machine learning models trained to identify mentions of entities within raw text. Finally, in the top left part of this schema, we can see the structured data. In this case, it represents the HR position hierarchy, where you can see the positions, who reports to who, which roles they have within the organizations, and so on. The way this structured part is mapped with the unstructured part is through named entity recognition, which was fine-tuned to be able to identify position mentions within the documents, hence the mentions position relationships between the document and the position. So let's start exploring the graph by going to the visualization. Here we see again the schema view, this time enriched with additional information in the form of these black badges with numbers. They are the counts of how many of these nodes and relationships appear in the document. So you can see we have roughly 800 documents in the database, and they have 95 connections to, say, criminal charge named entities. When we visualize this part of the graph, we can see that there are documents connected to entities such as torture or intimidation, harassment, misconduct. This demonstrates that by combining machine learning with graph databases, we can surface implicit connections which are based on the knowledge previously hidden within the data. We can also explore the whole document structures. Within the regulatory compliance domain, the documents tend to be naturally highly connected, as you can see in this graph. Just by looking at this by eye, you can hardly find any insight. And now imagine that we are doing a review or an audit. Like, where would we even start? Well, one of the options we have is to leverage graph algorithms, which analyze the graph substructures and allow us to view the same graph from slightly different angles, depending on which algorithm we use. For this task, we used the Graph Data Science Library, which is the analytics engine of Neo4j's enterprise graph framework, which was built for data scientists. And we used, for example, centrality algorithms such as PageRank. So when we visualize this, this graph, where the nodes are being, node size is being scaled by the PageRank scores, then you suddenly start seeing some structures and some first insights. As you might know, PageRank was discovered by, or was introduced by Google Search as a way to rank the importance of web pages on the internet. It works as a sort of popularity contest where the importance of a node is being, or is dependent on number of incoming links and the importance of the source nodes of those links. And immediately see that there are several entities or several documents which are deemed very important from this perspective. So it gives us a clue where to prioritize in case we are doing a review, for example. Alternatively, we can use a different centrality algorithm such as betweenness. This one gives us a slightly different view of the same graph. Between centrality estimates the rank or ranks the nodes based on the number of shortest paths which pass through these documents. You can think of these nodes as sort of bridges. They typically connect different graphs substructures which would otherwise be very loosely connected, or even could become disconnected if these nodes didn't exist. Typically, this is a very useful algorithm for complex supply chains where it can identify bottlenecks. Here we can see that it identifies a couple of documents which serve as a bridge towards a certain domain knowledge represented as a cluster, which would otherwise could become disconnected from the main corpus, and therefore we might perhaps lose some important domain knowledge. Now, let's say that after observing this graph and after doing some initial review, we noticed that some of the documents or some of the information in the documents or in the parts of the regulation guidelines are duplicated or spread across too many sources. This is fairly frequent, especially in the regulatory compliance domain. And what we might want to do is to consolidate our data structure so that we avoid issues such as reduced productivity or people working with out-of-date information, or even worse, out-of-date instructions. So let's take a concrete example. Let's take the guideline on recruitment. And we can expand here. What we are basically looking for are similar documents or documents discussing similar topics. So here, what we visualized are virtual relationships towards documents that are somewhat similar. They are virtual, these relationships, because they are not stored in the actual physical database. They are just a mere projection of the actual graph, and they work as a sort of simplified layer, which helps people or humans or analysts to reach the decisions more quickly. But knowledge graphs are also very good in the sense that they can be fairly easily configured to be explainable. So typically we would like to know why this connection is deemed important or significant. And you can see that in this simple example, we used a keywords algorithm, which found that both of these documents talk about the similar concepts like assessment process, role scope, ISSQX employees, and similarly we can inspect the other documents. Of course, this is a simplified way of looking at the similarity. In a more advanced scenario, we could basically use or evaluate the semantic similarity between the documents, or ideally between the parts of the documents, like individual sections or even paragraphs, using, for example, topic modeling techniques. All right, so so far we discussed knowledge graphs as they would be sort of static. In the real world, this is actually rarely the case, especially in the regulatory compliance or when we model any big organization. Typically, things change in time, and understanding this change, and especially the impact of this change, is critical. So here we can take as the example the structured data, which is the positions hierarchy within the company. This hierarchy evolves over time as people join the company. Some people leave, some people change positions. This hierarchy currently is displayed in the whole range. However, we can also view it at a different time snapshot. So we can see, for example, that in May 2020, the hierarchy was much simpler. Then there was a pretty significant update in July 2020 and further update a few months later. So this demonstrates that the knowledge graphs can be dynamic, and a visualization can be one of the ways to model or to view, to explore this, this behavior. Let's take a concrete example of this temporal aspect of the knowledge graphs. Here we have again the guideline on recruitment, which was ingested, parsed, metadata were extracted, it went through the NLP pipeline. So we, for example, know that the guideline on recruitment is owned by Manager People Safety and Security, or that it was authorized by or approved by the CEO himself. Now, what you can notice here is that this entity node has a red blinking badge. Why is that? Well, as we mentioned, the knowledge graph contains both structured and unstructured data. And it noticed that this role, this position within the organization doesn't exist anymore in the latest hierarchy. It is being outdated. That's why the red badge. So what can we do about it? Well, you might know that knowledge graphs are a very good tool for building recommendation engines. So in this case, we implemented a very simple recommendation, which, okay, I forgot to turn over the time bar. Okay. We implemented a very simple recommendation, which shows us what actually happened. You can see that the Manager People Safety and Security was in the hierarchy in 2019. However, what it might be replaced with is Manager People and Culture, which was introduced in 2020. So this is one way of looking at this graph. Now, once we have this, and we start changing or updating the documents, then we have to be careful here, because as we discussed, these kind of documents tend to be highly connected. So a change in one of them can have an impact on loads of other things. Therefore, understanding and doing the impact analysis and understanding these impacts is important. So one simple way how we can do it is we can find out which documents are referring to our guideline on recruitment, because that can mean that if our guideline is outdated, then this guideline on conflicts of interests might need revision in certain parts as well. And similarly, we can define a action where we inspect basically the documents to which the guideline on recruitment refers to, and see if some of them are perhaps outdated themselves. And actually, as you can see, there are 3 of them which are found to have multiple positions which are either outdated or even discovered. So they are mentioned in documents, but they don't exist in the hierarchy. And this is very important. It gives us basically 2 main conclusions. First, we should obviously review these documents and make sure that they are up to date. And second, it gives us a feedback for the guideline on recruitment, which in certain parts might need revision in turn. All right, that's it for the demo. I hope you found it useful, and back to Michael.
Thank you very much, Vlasta. I just wanted to conclude with a slide. Eva, if you can upload them. Oh, there they are. Okay, good. Great. So to summarize, you have seen a short sample demonstration of how we used knowledge graphs and Hume to help a regulated government organization with their regulatory compliance challenges. We have implemented a solution that addresses traceability between legislative and organizational obligations and compliance instruments. You have seen some automated impact analysis, some similarity identification, also the identification of gaps and outdated references, and also a simple recommendation to do something about these changes, right? And finally, hopefully it was clear that this tool or a knowledge graph in this form allows non-technical users to gain some insights and answers from densely connected compliance-related data. So with that, I thank you very much. Hopefully we have managed to convince you to consider knowledge graphs for looking at some solutions for regulatory compliance challenges. And I think we're ready to take a few questions.
So there were a few questions during the webinar. Most of them have been answered on the go. Maybe there's 1 or 2 you want to come back to, Michael, or something you want to explain a bit more in details?
Yeah, so so one of the questions that popped in was, what's the difference between Bloom and Hume? So Neo4j's own visualization tool, where I kind of try to explain this, but it's for a longer conversation. Well, Bloom is a perfectly capable visualization tool on top of Neo4j. Hume is, I would say, much more than that. It's a whole platform to allow you to build knowledge graphs and explore them and get some insights from the data. And I think one of the biggest differences I try to describe in one sentence in the Q&A panel is that by having schema, the screen you have seen that Vlasta showed, where we define what our domain is, what our problem is, what is it we're trying to do, you're abstracting away from what's in the database, right? So many visualization tools out there will force you to change how you store the data in Neo4j in order to visualize them the way you want. In Hume, and you have seen this in a concrete example of this virtual relationship that Vlasta showed, which he later explained, is that you can take shortcuts in the graph. You can create a completely different perspective on the same data for different users whilst maintaining the graph model in the database the way it should be, right? So that level of abstraction, I think, is very powerful. We can compute on the fly relationships, attributes, and things like this. And it's just one of the many differences. The other thing, one last thing I'll mention, is that Hume basically includes an entire ingestion workflow with enrichment and some machine learning capabilities, as well as other things like temporal analysis. You've seen the time bar, but there's geospatial features and things like this as well. So I think that kind of summarizes the main differences, which is what I wanted to elaborate on and see if there's any other questions that popped up in the meantime.
Yeah, we just had a question. How do you combine automatic knowledge extraction with manual additions?
Right. So you have seen when Vlasta was running some of these actions, what he called actions, which was essentially like running the recommendation or something like this. Under the hood, these actions are very simply pre-canned cipher queries. And these actions can optionally take user input. So if the user was to modify the graph manually, you simply configure an action that will allow them to take input, and they can maybe create connections. They can change attributes of nodes and relationships. And of course, in the background, what you typically want to do in a real life scenario is to audit those changes. So you can build some logic in there to make sure that you know who changed what, right? And perhaps have a multi-stage process to make sure that if somebody suggests a change, then somebody else has to approve it and so on. And that's all possible to configure in a system like Hume that would manage a knowledge graph. So we've showed mostly the automatic ingestion capabilities, but there are possibilities to allow humans to enter the data manually.
Thank you. I think that was pretty much it for the questions. I'm just seeing a comment about the book. If you fill in the form, you should be able to access the link directly, but otherwise we'll make sure we also share that in the follow-up email. Thank you everyone for joining today. So as I was saying, recording and slide will be shared later via email for anyone registered. Thank you, the GraphAware team, for this amazing presentation. And on that, I will stop the webinar. Thanks. Bye.